Laboratory fume hood performance testing is an interesting field in that there's a lot of misconceptions. So hopefully today you'll pick up something in terms of understanding the difference between what's real and what maybe isn't. But we'll get started. So what's the purpose of a laboratory fume hood? It's basically an exposure control device. It's basically a device that's intended to protect the user from the bad stuff that's on the inside that they're working with. So it's basically a device. It's oftentimes considered to be an engineering control, but in a way it's also a PPE. So it's a sort of a hybrid device. Unlike other types of devices like a biological safety cabinet, a fume hood is definitely not a standalone device. It's a device that is really the interface between the user and the mechanical system. And the best fume hood in the world does nothing without being connected to a properly designed and maintained mechanical system. There's three components that we like to look at when we look at fume hoods. One is the fume hood design. One is the laboratory ventilation system, and the other is the user and the user's work practices. So how do we know a fume hood is performing safely? And this is where part of the misconception comes in. It's really not about face velocity, it's about containment. If the hood's not containing, the hood's not working. So regardless of what the face velocity is or isn't, a loss of containment is a failure to perform. Face velocity does not indicate or predict containment. So, in fact, in all the hoods we've tested, 70% of them that fail to contain actually have acceptable face velocities. So if you're using face velocity as a metric for determining the safety of the hood, you're really not going down the right path. So we need to be looking at containment rather than face velocity. So what does it mean? Is your hood working properly? Well, again, it's all about containment. If the hood's not containing, it's not doing what you're paying for it to do. And, a lot of times people say, well, we can't afford to fix it. And I'm like, well, then turn it off because you're wasting energy. If it's not doing what it's supposed to do, why waste the energy to run it? So why do hoods fail to perform safely? And there's three categories of failures. 25% are design issues, either hood design or laboratory design. Surprisingly, 50% are mechanical issues, room conditions, balance, supply air, other components that make up the room side. And 25% are caused by the user. They've overloaded the hood, they're doing things in front of the hood they shouldn't be doing, all this sort of stuff. So, unless we look at all three of these components, you're not going to have an optimized situation for hood performance.
Tricolor is a major upgrade from face velocity testing. Some testers will certify a fume hood as safe based solely on a face velocity profile. There's a major misunderstanding about face velocity. Many assume that if a hood has a certain face velocity, that it's properly containing. And this is simply not true. Take this hood for example. It's showing an acceptable velocity reading of around 100 feet per minute. Yet the hood isn't containing any smoke at all. Why? Because there's no direct correlation between face velocity and containment. I'll say that again. There's no direct correlation between face velocity and containment. For more on this, watch our YouTube video about the myth of face velocity. So we are simply building on top of the ASHRAE 110 protocol because a full-scale tricolor test still includes a face velocity profile and a small smoke or local smoke visualization test. But tricolor takes containment testing to a whole new level so you can be sure that your hood is performing and containing safe. With tricolor, the proof is in what you see.
And what was being talked about there is a process that we use, which is dynamic containment testing. And what we're doing is we're releasing a haze into the hood. And the problem even with smoke, if you're using a theatrical smoke machine, the velocity is quite fast coming out. In fact, oftentimes it's in the range of 1,500 feet per minute. So you're overpowering the hood. So what we do is we use haze, which is a diluted form of fog, and we very gently inject it up into the vortex. And that doesn't disrupt the airflow inside the hood. And then as a result, we can actually see what's going on inside the hood and go from there. Then we have lasers, both on the inside of the hood and the outside of the hood. The one that you saw where it said unsafe there was a green laser on the outside. And what that does is when the haze escapes the hood, it has to pass through that green light curtain, and it illuminates it and turns it green. So you can actually see exactly what a hood's doing. And I won't go further into it at this point, but I think that's really something that is worth looking at. Basically, there's a lot of stakeholders when you look at fume hoods, and we have administrators and financial people and maintenance people and facilities people and EHS people and lab managers and users. It's a pretty big group, and so if you really don't involve most of the group, you're not really going to get where you want to be. But there's a movement right now towards risk-based safety strategies, and we'll talk about that a little bit more in the presentation. This whole concept of face velocity is not new. I mean, we've known about it for many years, but there's a good article that we have. You can go to our website, fumehoodcertified.com/myth, and download the article. And it's got a lot of references to other people who've written about the subject as well. Although there's a growing consensus that face velocity cannot be applied as a sole evaluation of fume hood containment, it's something everybody tends to use. And a little bit of the history, and I won't obviously get into the details, but if you look at the fact that velocity alarms that we see on hoods today, why are they there in the first place? Well, they were there when we didn't have manifold systems, when every hood had its own fan. And the whole purpose of the velocity alarm was to tell you whether your fan was turned on or not. And out of that, we've sort of grown to where we are today. So the whole idea of looking at face velocity needs to be, reevaluated in the context of what is it really telling us. Also, it's very clear that as we get concerned about things like energy consumption, that the one-size-fits-all doesn't work. So we need to look more at risk-based systems and what the consequences of exposure are, and we're going to look at a standard here in a minute. So basically a safe hood is a hood that's containing at safe levels. But in determining risk, we have to consider other things like how often does a hood fail to contain? And I can tell you with 100% certainty, there is not a hood in the world that does not lose containment from time to time. I mean, it's just an impossible feat, so it doesn't happen. What's the magnitude of the leakage? Is it slightly leaking or is it a major leakage? And what's being leaked out? What's the fugitive chemicals that are coming out of the hood? And then two, how long is the user standing in front of the hood? So, I mean, there's a lot of different factors that go into a risk-based assessment. Few people really are aware of this standard. It's an ASHRAE standard, and it's guidance for laboratory ventilation design. And it's based on the same concept as your biological safety levels. So BSL 1 through 4, this is lab design level 0 through 4. So there's 5 classes instead of 4. And then here it tells you, so in a class 0, you don't even need a fume hood. Really, you don't need a decent hood until you get to a 2, but you need a really good hood for a 3 and a 4. So similar to what the biological safety is. And they have a definition. The standard is readily available on the internet. But they have a standard, and it's based on the class of chemicals you're using and all that. That's what puts you in these different classes. So this is something where we basically have, the higher the number, the higher the risk, and therefore we want to make sure that we're providing proper protection levels at these different levels of risk. Now, simply reducing exhaust flow isn't the answer, and unfortunately, we've put a lot of emphasis on energy savings, which is appropriate, but you have to look at it in a little bit different context. Because if we simply lower the face velocity, then we're probably, in most cases, going to increase the likelihood of loss of containment. So what are the takeaways about face velocity? Face velocity is indicative of air movement. And what you may not realize is that hood you saw in the video where all the smoke was coming out, that hood was actually running backwards. So it was actually blowing out of the hood at 100 feet per minute because hot wires are not directional. So they don't know which way the air is moving. So that's another concept. The other thing is face velocity readings are merely a snapshot. And I've got a whole session I do on face velocity. We're not going to dig into it quite that deep today, but it's something that really is worth thinking about. But there's another kind of containment that is often overlooked, and that's the physical containment. Things like chemical splashes, sprays, runaway experiments, small fires, minor explosions, and the sash is a user's best friend. Having that sash down in front of you is something that's going to make the hood work better. It's also going to protect the user a lot more. So many experts agree that the underlying problem is how to approach safety. So many people see it as a checkbox. It's a regulatory thing we have to do. We got to put a check mark by it, but they really don't get into what it is to create a safety culture and to operate the hood safely. So, a question that I always ask is, how many injuries or fatalities are too many? Is it 1, 10, 100, 1,000? Now, here's an example of an individual that was involved in an accident, and we would say he's lucky. He lost his lab coat. This guy wasn't so lucky. He was majorly burned working in front of a hood. Now, this is actually an educational setting. There are students here you can see their reflection there in an auditorium style thing. And it's a first year class and they're doing sodium. So the instructor, he's probably done this 100 times. He's going to take a little piece of sodium and drop it in the water, and watch what happens. Now, needless to say, that probably was not the planned outcome. And that's the way it is with accidents. You know, we may have done the same unsafe thing over and over and over and been lucky enough not to have that sort of an event. But, you know, you just don't know when it's going to happen. This is another concept where the stash is very useful. It's called flame jetting, and that's where you have a container that's got flammable in it, and the fire gets in underneath it, and then it just blows all the flammable liquid typically out. And so that's not a good scenario either. But you know, even a small fire can cause hundreds of thousands of dollars in property damage. And the sad part is there's been a lot of people working on PhDs that dropped out because they lost all their research. So, you know, it's not just the building. But there's a really good article. This is from the University of St. Andrews in the UK. And there's a web address at the bottom, but it's the anatomy of a fire. And if you really want to get a better understanding, a better appreciation, this is a real good article to look at. Now, this is China. This is a security video. And it's about 4 minutes long, but we're going to watch it all, and I'll kind of talk. So you see there was an event in the hood. We saw a flare-up. The young lady was not injured in any way. You can still see that there's a little bit of fire or something, you know, flaming from time to time. Now, her coworker there, they're standing there looking at it. They don't have a clue what they're doing. They're basically, they don't know what to do. So they've not been properly trained. They probably don't have an SOP on what to do in the case of something like this. And so this is a very minor incident. I'll go ahead and give you the spoiler. They burnt the lab completely down. So what should have been a very controlled situation that was minimal damage ended up totally destroying the lab. So what's happening now is that this is still got an ignition source and it's building up heat. So the fire triangle is working its way up now. So we've got heat, we've got combustible vapors. And, you know, what's really interesting here is, you know, they're like the guy now after 2 minutes in, he says, well, maybe we should unplug it. So they unplug it. But they didn't do what they should have done, which was get a fire extinguisher and put it out. So, you know, they're still talking about it. They're still trying to figure out what should we do. And you can see now the bursts are getting more frequent. And when they do, you can see the orange color. And what that's telling you is we have combustible gas building up fuel. So the fuel is building up on the inside of the hood, and it's, you know, it's a disaster just about to happen. And in the very last bit of this, you'll see what happens. But, you know, it's still going on. So this goes from minor to major in 4 minutes. So this is an event that, you know, with proper training and everything, probably could have been minimized or prevented. So again, you see that, you know, we're getting more and more flare-ups. So we're about 3.5 minutes into it. So we're getting close to the finale. But the finale is worth waiting for. I mean, they're really struggling trying to decide what to do now. This is someone else who comes in finally with a fire extinguisher, and what you'll notice is the fire burned through the roof. So it's come out the top of the hood now, and it's basically set the whole lab on fire, and you can see it flaring up there in the corner, and then very quickly you're going to see that the entire lab just fills up with smoke. But this lab was totally destroyed. So there now it's a major fire. So what went wrong? You know, do you think they had an SOP? Probably not. Do you think they understood what to do? Probably not. You know, and the question really is, do you think if they'd have been properly trained that you'd had a different outcome? And I would like to think yes. Don't know, but you know, we would hope so. But I've been doing this for 40 years, and I've unfortunately had the opportunity to visit many places that have had bad events. And trust me, you don't want to go there. It's not a place that's good. Another thing that comes up quite frequently is that I have a hood, doesn't it protect me? A lot of people just assume they walk into a lab, there's a hood there, it works. Well, there's been various estimates, but probably somewhere between 50 and 70% of the installed hoods in the US do not contain properly. It's a huge number. And so, you know, we're creating a lot of potential health problems down the road. But you know, it's really, if we're not concerned about safety, if we're not concerned about protecting the user, why have the hood in the first place? Well, okay, so the regulations say we have to. But you know, it's something where we've sort of lost our focus on user safety. Now this is an event that happened at University of California, and there was about 12 years ago now, there was a young lady, she was working with an air reactive chemical and was pulling it out of a container in a syringe. The syringe popped out and caught on fire. She didn't have a lab coat, and she was a graduate student, by the way. And her sweater caught on fire, and she died from the burns. Now, her PI was charged with felony manslaughter, and it cost the university just for that $4.5 million just to get those charges dropped. Now, if you look at all the costs pertaining to that accident, they're closer to $20 million. So, I mean, accidents get to be very expensive. Now, this is St. Andrews, the one we looked at earlier, and it was just a relatively small fire. There it was right at dusk in the evening. It started from a routine post-experiment wash-up. So they were cleaning something probably with a solvent, and it got to an ignition source, caught on fire. They did have an SOP, they did have procedures. As they would say in the UK, the fire brigade got there in 7 minutes, so very fast response time. But the big thing is, it closed that building for over a year. They had 122 PIs that were displaced for a year because of them having to redo the building. And so accidents are expensive. And you know, I've heard for many years, oh, we can't afford to fix that. We can't afford it. Well, guess what? You can't afford to have an accident either. So we really have to put it in context of, you know, saying we can't fix it is one thing, but can you afford to have an accident? So here you can see, look at all the lab notebooks up there that burned. So you can lose a massive amount of storage. Now, if you read the article, you'll find out they were doing a lot of life science in the building also, and the fighters had to turn the power off, and their sub-zero freezers got within 7 minutes of warming up to where they would have lost all their biological samples. So could have been an even worse disaster than it was. So here's something that the accident I was talking about at California was in 2009. It was right around Christmas time. And this is something that I think to this group in particular is worth looking at. The Chemical Safety Board only reports serious accidents. So there's got to be substantial damage, substantial injury, or death. So in an 18-year period, they logged 262 accidents that resulted in 490 serious injuries and 10 fatalities. That's a lot of people. But the thing that you should focus on is 81% of those were in the educational environment. Why does education have such a high accident rate? And it's my opinion, it's largely driven by training, that we don't spend enough time training people to minimize that likelihood. The report is out there. It's a who's who. I mean, there's probably not a university of significance in the country that isn't on the list. So this is not just a junior college somewhere or something like that. We've got the Harvards, the MITs, the list goes on. But it's something that really, and the reason they did this comparison here was they said, did we learn anything from Sherry's death? So they looked at the years before, 8 years before, 8 years after. There were 3 extra accidents after. So the answer is we didn't learn anything. It's just as bad today as it was when it happened. So I do a lot of presentations overseas, particularly in China, and I tell them, you don't want to be part of my presentation. You don't want to be a statistic because statistics about accidents are not good. So it's much easier to take corrective action and fix it than it is not to. So, there's the legal and regulatory requirements and all that, but it's really about protecting the people. I mean, that's really what it's all about. Yes, we have to comply with all the stuff, but you really don't want to have an accident. So the cost of an accident is very high, and generally speaking, if someone is seriously injured, you're looking at settlements in the neighborhood of 10 million plus per person. And so it's something that you really have to really have to think about. Now, I hear a lot of times people are talking and they say, well, our hoods pass ASHRAE 110. Well, they don't, because ASHRAE 110 is not a pass-fail standard. It is a testing protocol. And then you have to go elsewhere to figure out what is a safe level. And ANSI Z9.5 is the most common place to go to look for that additional guidance. But, in my mind, what makes 0.10 leak rate of FS6 safe and 0.11 parts per million unsafe? So it is a method, but it really doesn't tell you the whole story. So testing really helps ensure compliance with the regulations. but it also helps us understand the problems. And my company, we have a software package called Fume Hood Performance Tracker, and it's basically modeled after the maintenance log in a commercial aircraft. So, you know, people say, well, what do aircrafts and fume hoods have in common? Well, they actually have a lot. But in this case, they're going to be in service for many years, 10, 15, 20, 30 years. They're going to have lots of users, pilots for the planes, chemical users for the hoods. And so when you look at why does a maintenance log exist in the first place in an airplane, it's so the pilot can get in and look at it and have a comfort level that that aircraft is safe to fly. So wouldn't it make sense that you'd want the same degree of confidence for your users using the hood? And then the other thing is we use a lot of video, and because of that, that really helps support you if you ever do have a problem. It's a QR code-based system, and you shoot the QR code, and almost every problem that we try to solve, we look to other industries to see how did they solve it. And one of the most common things we started seeing was get in the elevator, and you're going to look over at that certificate, and it's going to say certificate in engineer's office or something. They're not going to put the real certificate there anymore. And the reason was there were so many outdated ones, you didn't know if there was a newer one that just didn't get posted. So we do the same thing. We create a digital certificate, and the digital certificate is available by shooting the QR code. So, as I said, I did a lot of international work, and back in 2020, when that sort of dried up for a while, I finally finished a book I'd been working on for a long time, and I basically tell people don't buy the book. We've converted it to a free online course, and it's written in very simple language. You don't have to be a HVAC person to understand it. It's written so that all the stakeholders can get a very holistic view of what fume hoods do and how they work. So I would encourage you to check it out. I know a lot of members of this group have already taken it, and feel free to encourage others to do the same. For us, it's more about getting the knowledge out there than anything else. And I think most everybody that's read it has been very positive about saying that they were able to get something out of it. So anyway, that's my presentation. And I cut it a little bit short intentionally because I wanted to give everybody a chance to ask some questions. So if there's any questions that you have, I'd be more than happy to try to answer them.